Welcome to my talk called Physical Units for Matrices, where we'll be taking static type safety to the next level. My name is Daniel Withopf. I work at Bosch. If you don't know, Bosch is one of the biggest car suppliers in the world, and I mainly work on automated driving, so self-driving vehicles and driver assistance. And also more recently, I worked on base libraries, so this is the topic of today's talk. It will be a little bit interactive, so I have a few questions for you in the audience. If you could answer them, that would be really great. Okay. Would help me out. If you have questions, also feel free to ask them during the talk. Longer discussions will probably better move towards the end. So let's see what's in it for you today. We'll be mainly talking about physical units for vectors and matrices, as this is the title of the talk. It might be surprising, this might sound like an easy topic, but actually this problem has never been properly solved in C++, nor in any other statically typed language before. So it's fairly complicated. But even if you're not interested in this topic, there's a lot you can learn today about static type safety in C++ and library interface design. We'll try to achieve what I consider the ultimate goal in library interface design today, which is given by this one sentence: if it compiles, it works. So let's see how far we get there. What do I mean when I say if it compiles, it works? So in the talk, we'll follow a few overarching design principles. So we'll try to anticipate problematic usages and prevent all of them at compile time. This will go so far that it almost feels like a built-in static analyzer for the C++ type system. So effectively, it's your math and physics teacher built into the C++ type system. I hope you all have good memories of your math and physics teachers from back in school, otherwise it might be difficult today. So on the way, we'll also try to enable the users of such a library to make sweeping changes in their code base that works once it compiles again. And last but not least, we want to try to make the user code that uses such a library as expressive as possible. So ideally, you should be able to tell from a single line of code what is happening there. Good, before we start, a little bit about the terminology. So if you don't have a big background in physical units libraries for C++, that's not a big issue. The main thing to keep in mind here is that you can think of them as being strong C++ types that behave exactly as you would expect. So for example, you can add two physical quantities with a unit of meters. You cannot add two physical quantities with a unit of meters and seconds because they don't match up. And you can multiply any two physical quantities, regardless of their units, together and end up with a valid physical unit. So that should be enough as a mental model for today. If you want to know more about the background, there's a proposal for the standard library, P1935, by Matrices, who also gave a talk earlier in the conference. You can check out one of his excellent talks, read the proposal. Yeah, you will find background there. So for the terminology today, so in classical linear algebra library, we talk about vectors and matrices. It should be simple. Vector is anything that's n by one dimensional, and matrices is anything that's two dimensional. In classical math, the notation is a little bit different. There you have points, which reside in a vector space, and you have displacement vectors, which give you the connection between two points. And of course, there are also matrices. My model today is a little bit similar to the mathematical model, so I will just try to distinguish between displacement vectors, which I call delta vectors, or they get a delta vector tag in my library, and points in the mathematical sense, which get a vector tag. And of course, there are also several matrix types. We will learn about these later on. Now let's see how we can combine linear algebra with a physical units library. As I mentioned, for physical units, there's P1935 by Matrices. For linear algebra, there's, for example, Eigen, there's a Blaze library, or P1385, which is also a proposal for the standard library. Now, this code example here shows how we can use the two libraries. The first code line creates a physical quantity with a dimension of length and a physical unit of meters. And the second line, that's taken from P1385, creates a three-dimensional vector with a scalar type double, and you simply list the three elements that you want to create. Now, first question for you. Do you have an idea how we can combine these two libraries? So if we want to create a vector that contains physical units. Do you have an idea how we could achieve that? The easiest one. The answer was just put the type in the vector. Yes, you can use the value type inside the vector. That's, of course, a fairly straightforward solution. And that also works in this case. So this is shown in the example here. Here we have an fs vector, and the value type is now a physical quantity with a length dimension, a unit of meters. Then you can add these two vectors here, u and v, together, and that's a valid operation. And if they would have incorrect units, it wouldn't work. So that's fairly easy. If you have uniform units, so all entries have the same physical unit, then it's easy, no brainer. Now let's move on to a slightly more complex example from my application, self-driving vehicles. Let's try to track a vehicle in one dimension. So this is a fairly easy example. So we'll only estimate distance in meters, velocity, meters per second, and the acceleration in meters per second square. Now we try to create such an fs vector here. On the right-hand side, we have a 1 meter as the first entry, 2 meters per second as the second entry, and 3 meters per second square as the third entry. But now the question is, what should be the value type of that vector? So these are different types, as we said. We have strong type safety, so meters and meters per second is a different type. So it's not possible to name the value type here. Does anybody of you have an idea which other C++ data type we could use to represent this? So if you have different types that we want to store in a container. Sorry? Variant, yes, variant is one option. So we could use a variant as a value type. The other option would be to go in the direction of the tuples. That's the second option. Both is possible, but it makes the code really, really complex. And you also no longer like writing a linear algebra library. For example, Eigen has very nice optimizations for everything. If you would use the tuple or the variant, with variant, you would have to use visitors all the time, which is very inconvenient and compile time overhead. With the tuple, you would have to write all your linear algebra by yourself. So not a good option. Plus, we also see here on the next slide that it's a little bit different. So it's not a tuple with n elements. So in this slide here, we have a 4x4 matrix. And such a matrix can, in theory, have up to 16 different physical units inside it. So now imagine a 10x10 matrix with 100 physical units. If you want to have a tuple with 100 elements, it gets really complicated. Fortunately, the problem structure is a little bit simpler than this. So the units in the matrix are not completely independent, but the only independent parameters are the row units R and column unit C listed here. And then the individual units of an element are given by a combination of the row unit and the column unit. Can be a multiplication, division, we'll see later on. So we'll have a full taxonomy later on. In general, it's a combination of the two units, row and column unit. Now, I will also want to explain a little bit how I started my activities on the topics and give a motivation why I started it. So in our code base, when you use linear algebra code, there are often code lines like this here, where you have a measurement vector, you access it at index 2, and you access other vector at index 3, and you want to assign the two to each other. Now, for such a code, I immediately have two questions. First of all, what do the vector entries describe? Because there's no mention of what's at index 3 in other vector or what's at index 2 in measurement vector. Furthermore, this could even be an out-of-bounds access, especially if you're not using compile time numbers here, but runtime numbers. So in the next try, maybe the code has been rewritten, and the code now looks like this. So we now use enums, scoped enums, hopefully, here to access the vectors, and we now access other vector at position x index and measurement vector at velocity x index. Now, when I see code like that, again, there are two questions. First of all, have the right index constant for the respective vector type been used? Because there's no guarantee that position x is meant for other vector and velocity x index is meant for measurement vector. So they might be completely unrelated. And second of all, this is also where your physics teacher comes into play, is assigning a position to a velocity really something that's a correct operation? Most likely not. So this is probably a bug. And in the last try, maybe the code line looks like this here. So we access other vector at velocity x index and assign it to measurement vector, also at velocity x index. In that case, this looks okay, but there's still one last question remaining, namely, in which coordinate frame are the two indices or the two vectors? Because if they are from completely different coordinate frames that have a different origin, then again, this is most likely an incorrect operation. Of course, if they overlap and have the same orientation, then this would be okay. But in most other cases, this is problematic. So from that, what I explained before, I came up with my linear algebra library wishlist. First of all, I would like to have an out-of-bounds protection at compile time, so not at runtime, but ideally you can't even access a vector out of bounds. Second of all, I would like to have expressive and enforced names for vectors and vector and matrix entries, so that you can't access a vector at position 2 without specifying what's actually contained in that index. Furthermore, I want to support non-uniform physical units in vectors and matrices. So as we've seen, the uniform version is fairly easy. You just can use the value type of a vector, but the non-uniform one is more complicated. And I would also like to have a physical units check at compile time for all matrix operations, meaning we should make sure that the physical units of the matrix operations match up. And as we'll see towards the end of the talk, there's actually a much harder check that we should enforce, and I will show how this can be done. So it's not only about physical units, there's much more to the problem. Last but not least, I also would like to have coordinate frame annotations for all vectors, matrices, and for transformations between vector spaces. So this was sort of the prelude, the motivation. And now I want to move on to the actual solution space, how it looks inside the library and what you need to solve the problem. So the first ingredient that we need to identify our indices are what I call named index structs. These named index structs identify each entry in a vector or matrix with a unique name. So in this case, I picked dxc, which stands for distance x. The c means Cartesian. That's the Cartesian index. Such a struct is created by deriving from a base class, Cartesian index type, and you specify as first argument the coordinate frame. So this is the vehicle front axle coordinates. So if you're in a car, it would be the ego frame. Second one, the second template argument specifies that this is the x-axis in that coordinate frame. And the last argument specifies the physical unit. This has a physical unit of meters. Now we can also create different structs and different coordinate frames. This here, dy sensor, would be the y distance or position in sensor frame. And you simply list the different coordinate frames, say that this is the y-axis, and again specify the physical unit. So as a general rule, what I did here, these indices have three parts. So they consist of a distance, a physical quantity specifier in the beginning, distance, velocity, acceleration. We have an axis identifier in the middle, x, y, z. And the last part specifies the coordinate frame. Now I should also mention why dxc does not contain a mention of the coordinate frame. That's why the reason for this is because in our project, the vehicle front axle frame is the most common frame. You use it very frequently, which is why I left out the coordinate frame name in this case. But of course, all of these are just structs that are empty. You can create them by yourself. So each user can define custom name. You can switch to different casing and not use macro casing here. That's all up to you. They should be ideally speaking names that tell you what is the content of this index. That's the only condition. Good, now I want to move on to the first types that you need for such a library. The type is called exactly as the library itself, type-safe matrix. And this library type has 4 template arguments. So the first type is the scalar type. Do you want to have a float, double, or integer scalar type? Second argument is the row index list. This is a list of these indices I showed earlier that tell you what the rows describe in such a matrix. The third argument is a column index list that describes the columns. And the last argument is a matrix tag. I will show later on what that exactly means. This is used to distinguish between points, vectors, Jacobian matrices, covariance matrices, and stuff like that. So we not only have an annotation for the units, but we also know what kind of matrix this is, which will be fairly handy when we later on want to check all our vector operations. And the only member in that class is an eigenmatrix in that case. So I have different bindings. I also have one for place and for our in-house library. And that's simply an eigenmatrix here with a given scalar type. And we take the size of the rows in the column index list as the size of the matrix. Fairly easy. Then there are certain aliases. So this here would be a type-safe vector, where you only have to specify the rows. So in this case, the columns here are given by a type list with a no index type. And this is simply a sort of empty tag. This means that this index does not influence the physical unit. So the column unit in a row, in a column vector does not influence the physical unit. The only important information is contained in the rows. And then we have an alias for our first position vector in vehicle frame here. This is a three-dimensional vector that uses the dx, dy, and dz indices that I showed earlier and specifies the vector tag. So this would be a point or position vector in vehicle frame. Now I want to show how we can create such a vector and how we can access its element. So when we create such a position vector of dimension 3, we simply list the 3 elements in that case. And there are different ways how we can do that. So the first and most type-safe one, the 3-star version here, is to call the entry method. And this entry method extracts the given index, so in that case, the x position index from another vector. And then in that construction, it's assigned to the x position index in the current vector we're constructing. The second and a little bit less type-safe version is to use the rep coefficient SI method. And here you can simply specify a physical quantity. So you say, okay, I want to create a physical quantity with unit meters and use the value 1 for that. So this checks the physical quantity only, but not that sort of, you have to specify which index it is with a dy template argument. So it's still type-safe, but not as type-safe as the first one. The last version, the least type-safe one, is to use rep coefficient. This is sort of for backwards compatibility. There you only give a scalar, so you don't have to mention the physical quantity. In general, I recommend to users to avoid that because it loses the type safety. Maybe if you want to set an element to 0, then it makes sense to do that, but otherwise use the other ones. Now the same thing can be done when we want to read or write from a vector. So when we've constructed it, we can then use the assign entry method to assign an entry and the entry method to read an entry from another vector or matrix. And this is again the most type-safe version. So there's a check that dx is actually contained in other position. There's a check that dx is actually part of position vehicle, so the vector that we're assigning to. And if any of this would be untrue, then this would fire a static assertion. Oh, and I should also mention in the first case, the 3 elements have to be listed in the correct order. If you mix up the order, then this also gives a static assertion, which will be important for later. And then the second option here for reading and writing, that's a little bit less type-safe, is to use coefficient SI method for reading and coefficient SI ref method for assigning. So in this case, we can assign the y position in one frame to the x position in a different frame. This is possible because this only checks the physical unit, and the physical unit matches up. So the first one checked that the indices are identical, and here only the physical units check is done. And the last and least type-safe version, of course, is to use the add method for reading and writing. So there you only have the check for the scalar type. So here we can assign a velocity, y velocity in sensor frame to an x position in vehicle frame. Again, most likely an incorrect operation. So this should be avoided. And I also want to mention why in the second case, I'm using that coefficient SI ref method for writing and coefficient SI, a different method for reading. That's because I have to return a proxy type for the access here, or for the when you want to set an element, because I'm not actually storing physical units. I'm just giving the impression to the user that the matrix stores physical units, because that makes it much easier for eigen, for example, to do its optimizations. Good, there are more ways how you can create such a vector matrix. In this example, the first two elements are created by extracting the first two elements with a head method from another velocity vector. Then we multiply that velocity with a duration in seconds, and the velocity multiplied with a duration gives you a displacement. And these two displacement indices can then be used to initialize the first two entries in the vector we're constructing here. And we're listing the last element manually here by a call to entry dz sensor. So it's also possible to use subblocks and construct a full matrix from different subblocks. And again, we always have the full check. So if any of these types wouldn't match with the indices that are expected in the constructor call, user gets a static assertion. This also generalizes to 2 dimensions. So in this case here, we're creating a covariance matrix, a 2-dimensional matrix. The indices are x position and x velocities as both rows and columns. And then you have to mention both row and column unit when you call this method. So we call rep coefficient Si here with the 2 indices. And you have to list all the elements in row major order in that case. And as I said, it's also possible to create a matrix from blocks. So in this example here, for example, you could create the matrix from 4 or n columns, from n rows, from 4 smaller blocks, or from 3 rows and 3 smaller blocks. All of that is possible. Now the syntax here might seem a little bit verbose because you have to mention everything each time when you're constructing something. That's true. But on the other hand, this also enables a few nice features. For example, I did that in our tracking code once. You can exchange the order in your matrices. For example, I don't know, reverse and put the velocity first and then the position. This is possible. And because the library has so many checks built in, you will get a lot of static assertions if you do that. Then you have to fix all the places where you get a static assertion. And once you're done, there are no bugs left over. So I did that and there weren't any bugs because the library checks everything. So if you don't input the incorrect numbers, the order or so of all the elements, that's completely checked. So the only way how we could produce a problem when you reorder something is when you call that head method here, because that doesn't explicitly list which indices you're using. So if you call head and then call, for example, the norm on that resulting vector, this is something that might depend on the order of indices, but that would be a simple fix to also require the user to manually list the indices here, and then it's completely type safe all the way through. So I think that's a nice example of my sentence from the beginning. If it compiles, it works. So you get a lot of static assertions if you do something wrong. Good, now I want to explain how we access the elements of a matrix and what the resulting unit should be in that case. So what we're constructing here is a Jacobian matrix. So maybe just look at the picture here on the right-hand side. So the rows describe the measurement dr, that's a radial distance that could be from a radar sensor, so distance to the next vehicle target that has been found. Mesh vr is the radial velocity in meters per second, and mesh angle in radians is the angle to the target. And the columns are simply the x, y, and z position in vehicle frame with the unit of meters. So this Jacobian matrix gives the Jacobian of the row units with respect to the column units. Now, another question for you. Which physical unit should be returned if we do this access here? So if we call it coefficient Si, and we access the row with a unit with an index mesh vr, so the radial velocity with the unit of meters per second, and the column here with a physical unit of meters. Does anybody have an idea which unit should be returned here? In this case, so the Jacobian row meters per second and the column unit is meter. I can also give a small hint. The Jacobians are usually derivatives, and derivatives can be approximated by a finite difference quotient. So you're dividing things. Does anybody have an idea now? If not, just guess. Or I'll just answer if nobody dares to answer. So as I said, it's a difference quotient. So we're dividing something. So the answer is fairly simple. You just divide the meters per second by meters. So 1/second divided by second is the result of that unit in a Jacobian matrix. Of course, it depends. It's different for other units. We can generalize the formula here to all matrices if we introduce the notion of a row exponent and column exponent. So Jacobians have a row exponent of 1 and column exponent of -1. And if we use that, then the general rule would be to take the row unit, raise that to the power of the row exponent, which is 1 for Jacobian, and multiply it with a column unit raised to the power of the column exponent, which is -1. So we get a division. And this is the general result that holds for all different vector and matrix types. And I will show on the next slide what the different vector and matrix types are. So this is the full taxonomy of all vector and matrix types, at least the ones that I could come up with. So first group here are proper matrices, so covariance matrices, Jacobian matrices, and information matrices. In case you haven't heard of these, information matrices are the inverse of covariance matrices. What you can also see from the exponents, there are the inverse exponents of a covariance matrix. Then the next block are vector types. There we have position vectors, displacement vector, and again, information vectors, which have the inverse units given by the exponents. And the last block is what I called vector collections. So these are two-dimensional matrices that semantically contain vectors in their columns or rows. So you can have a matrix that stores n vectors, and then it's semantically a collection of vectors and not one of these matrix types. Good. Any questions so far? Doesn't seem to be the case. Then I'll move on. So until now, we've achieved unit-safe element access and out-of-bounds protection. Now the question is, can we do even more? And as it turns out, there's a lot more we can do, and we will learn that in the next part of the talk. So first of all, let's try to be unit-safe for all operations. So again, question to you, should this operation here be allowed? So if we have a vector that contains x and y position with a physical unit of meters, and we add a vector with vx, vy, so x velocity, y velocity in the same frame with a unit of meters per second. What do you think? Should this be allowed? No, I see. Well, was there a yes? Okay, can you elaborate why? Yeah, it's sort of, we'll come to that later. It has to do a little bit with displacement vectors, but here the physical units are not identical, so we're trying to add meters to meters per second. So in this case, it's not possible. What would be possible, that's almost your answer is pointing in the right direction. If you would multiply duration in seconds with that velocity vector, then of course it would again be possible. So next question, a little bit more complex. Should this be allowed here? So if we have a vector with a unit of meters, and we add a displacement vector also with a unit of meters to that vector, should that be allowed? So I guess I see people nodding. So in general, yes, this should be allowed, but this time it's not that easy. That was a little bit a trick question. So what if we have a position vector that describes x and y position in vehicle frame, and the displacement vector describes y and z position in the same frame? Then again, these vectors describe different things, and it should not be possible to add them these two together because the index types do not match up. And that's the important lesson to take home from that slide. Unit safety is not enough. We actually want index type safety if you want to be type safe all the way through. And again, I think this is a nice example of our slogan from the beginning. If it compiles, it works. Otherwise, you will get a static assertion. Now I want to show an example of a bit more complex operation inside the library and how this plays out. So here, in that code line, we're taking a covariance in vehicle frame in the middle of the right-hand side, and we're multiplying it with a Jacobian on the left-hand side and a Jacobian transposed on the right-hand side. This is usually the operation that you do when you want to get a covariance matrix to a different frame. And as you can see on the left-hand side, we're assigning that to a covariance matrix in sensor frame. Now I'm also showing down here the two matrices. And now I want to explain what happens when we multiply. So the first check that is being done is that the column indices of the covariance matrix in the middle and the row indices of the Jacobian transposed here are identical. That's the indices in the orange boxes. And we also check that the row and column exponents are the sign inverse of each other. And this means the physical units are identical because the indices are identical. The exponent is the inverse of each other, meaning they effectively cancel out. And we will end up with the column indices from the right-hand side that move over to the matrix in the middle. And then the exact same thing happens on the left-hand side. We again check that the index structs in the orange box are identical. The exponents are the sign inverse of each other. And if this is the case, they cancel out. And now the rows from the left-hand side are moved over to the middle. And as we can see now, we end up with a covariance matrix in center frame. So all the indices are in center frame. Here I ran out of space for dy and vx up here, but everything is in center frame now. And this is also what we assign it to. So we're assigning it to covariance matrix in center frame, meaning the operation was successful and everything is fine here. Now on the next slide, I also want to show what the addition operator looks like in the library. So this is the operator plus that accepts anything that's derived from matrix base, which is the common base class for all the types in my library. And the resulting type is a matrix expression. And such a matrix expression is a little bit similar to what Eigen, for example, does with matrix expressions. And that has two parts. So the first part, the promotion to the addition here, this is a promotion that promotes the type-safe matrix types to the resulting type. And the second part of the matrix expression, the second template argument, is simply the Deckel type of the addition operation of the underlying eigenmatrices or types. And this is responsible for doing the operations at runtime. Now I want to show what my promotion type looks like here. So in this case, the promotion to the addition is an empty struct that only inherits from a few base classes. The first base class requires identical scalar type. So this does what it says. It checks that the scalar types of the two expressions are identical. If not, the user gets a static assertion. Then we require identical row and column indices. They have to match up. And we also require identical row and column unit exponents, as I mentioned earlier. And last but not least, we require that the matrix tags are addition compatible. What that means is, for example, that you can add a point to a displacement vector, but you cannot add 2 points. That's incorrect math. You can add 2 displacement vectors or point to a displacement vector. And this is what's being checked here. And now I also want to show what such a requirement or a requires class here looks like. That requires identical row indices. Is again an almost empty class. The only content is a static assertion that checks that the 2 row index lists are identical, and it also injects the row index list for the results that we're doing in that addition operation up here. Now, as this is a template-heavy library, I also want to show what the compiler error messages look like. And what I showed on the previous slide, the structure with the base classes that I inherit from, that's a specific design to get really nice error messages. So when you do something wrong, so up here, the operation is we're adding a 3-dimensional point to a 2-dimensional displacement vector, so the dimensions don't match up, which should give an error. When this happens, you first of all get a static assertion because type identity checker failed. And now if we look at the instantiation history, we can see that this happened during promotion to the addition. So we already have the indication, okay, this happened when we added something. We then see, okay, it happened when we required identical row indices. So this operation requires identical row indices, but they weren't identical. And that then last but not least, the type identity checker template is instantiated. And we see that we have a 3-dimensional type list and a 2-dimensional type list. They are not identical, meaning the user gets an error. Now, if this reminds you of something, I should mention my library has been programmed for C++11. Of course, by now we have C++ 20 concept. So by now it would be better implemented with concepts. And here I have a brief example of what it would look like when we switch to concepts. That again gives you good error messages. So the main purpose of my implementation was to get as close as possible to what you could get with concepts out of the box. Yeah, for this I created an edible concept, and then you already get this nice error message. Good. Now I want to take a step back. Yeah.
Presumably compile times are something that's noticeable for this library because obviously it's template heavy. Have you noticed the difference between concepts and inheritance?
Okay, the question was whether I noticed a difference between what I did, inheritance for the requirements, and concepts. I didn't go that far. I tried it out with a few examples with the concepts, but I didn't do it all the way through. But as we are speaking about compile time overhead, I also compared plain eigen to my wrapping of eigen. And there, for example, when you multiply 5 matrices together, it was like 15% compile time overhead or something. So it's noticeable, but I think still okay. Good. So we've seen the implementation details before. Now I want to zoom out and talk about the big picture a little bit. So there's also a book back from the 90s called Multidimensional Analysis that actually describes most of the things that I did in my library. So the book is fairly old. I only found it after I was finished. And that's also where that picture is taken from. So here I want to compare the uniform matrix approach that we've seen in the beginning, where we capture or use the value type of a linear algebra library to put physical units inside that vector. So that's what I call uniform matrices here. And as you can see here in that slide, the uniform matrices are a fairly small part of the whole problem space of physical unit aware matrices. And my library type-safe matrix models the second outermost oval of multipliable matrices here. So you can see that we can model a much larger problem space because the units don't have to be identical in each of the elements. And we will now see that even inside that gray area here, where both approaches can model the problem, type-safe matrix models everything in much more detail and much more correctly. So there are lots of operations that cannot be prevented with the uniform matrix approach compared to type-safe matrix. I will show that now. So we'll have a look at what can be added or multiplied with the two approaches. So here, the table on the left-hand side shows the addition of two vectors, A and B, and we are looking at different options. So here, the first row and column is an XY position vector, second one YZ position vector, then we have an XY displacement vector, and a velocity vector, X and Y. And with a unit as value type approach, you can see here that all the operations are valid except the last column where the physical units do not match up. It's fairly natural because the only annotation we have available is the physical unit. So and with that approach, we cannot know what is contained in the indices. So there's also no way to prevent any of these operations. If we now switch to type-safe matrix on the right-hand side, the situation looks completely different. Most of the table has turned to gray and the operations are forbidden. So for example, here we cannot add 2 points, as I mentioned earlier. So these are 2 points that cannot be added. We also cannot add an XY point to an YZ point. What we can add, on the other hand, is an XY position vector to an XY displacement vector. That's possible. We also can add 2 displacement vectors with identical indices. And the last one, 2 velocity vectors with identical indices. And everything else is forbidden because it's also mathematically incorrect. And the same example now for multiplication. So we now want to multiply 2 matrices, A and B. The different options here are Jacobian matrices, Jacobian transposed, covariance matrix, and vectors. And as we can see here, all the operations are valid here because, as I mentioned in the beginning, you can multiply any 2 physical units and you get a valid result. And as the only annotation here is a single physical unit for a matrix with that approach, everything is valid. So nothing can be prevented. And now we'll see what that looks like with type-safe matrix. Again, fairly gray, the area. So most of the operations are not allowed. Here, if we look at that first block, this is the multiplication of two Jacobians. This is possible. I put a maybe here, but only if the indices match up in the Jacobian. So if the row and column indices match up and it's two Jacobians that we're multiplying, then this is possible. We can also multiply a Jacobian on the left-hand side with the covariance. That's what we've seen earlier. Or a Jacobian with a vector, again, only if the indices match up. You can also multiply two transposed Jacobians or a covariance with a Jacobian transposed. Good. Now, it should be obvious that this is sort of important here. Now, the most of the table here is gray, which means all of these boxes here, if that happens in your real code, then this is a bug waiting to happen. You've modeled your problem space incorrectly, and this is something that should be prevented as much as possible, which, again, is another example of if it compiles, it works. Now we've applied that slogan, if it compiles, it works. Until now, we've mainly applied it to the physical and mathematical part of the problem space. But of course, we're in C++, we're implementing a C++ library. So it's also possible to have bugs introduced by implementing something in C++. Now, question, I'm not sure how many of you have worked with linear algebra library before. Does anybody of you know what are the most common bugs when you work with linear algebra libraries? So if somebody knows the ranges library, do you know about the borrowed ranges concept? Okay, so I will explain on the next slide. So usually the two most common problems are, first of all, aliasing. So if the left-hand side overlaps with the right-hand side in an equation, for example, if you multiply matrices on the right-hand side and that overlaps with the left-hand side, then you're already setting elements on the left-hand sides that are still needed in the next operations on the right-hand side. This can produce incorrect results. So this is something that can be prevented. Out of time constraints, I can show today how this is done, but I can show how the second problem is prevented, and this is dangling references. That's something that happens fairly often. If you have a template expression-based library, you can easily get dangling references. I will explain now how this can happen here with example of eigen. So let's assume that we have an eigen method, calculate offset here, and that returns an eigen three-dimensional vector by value. Then we also have a pre-existing vector A here. That's just a variable that we declared. Now we can easily write code like this here, where we add vector A to the result of calculate offset, and afterwards we call the norm method to determine the length of the resulting vector. This operation here is perfectly valid. Everything is fine like this, but there's an easy way how we can change this. So just a small change and we get a dangling reference. So if we pull out these two, that equation here into two parts, so we first of all sum vector A plus calculate offset. We assign that to a variable sum, and then on the next code line we call the norm method on that sum method, on that sum variable. Then we have a problem. Does anybody have an idea what is happening here? So eigen is a template expression-based library. That means that when you do an operation, or when you seem to do an operation like adding the two vectors, it's not actually doing the calculations. It's creating an expression object that describes how this addition can be done. And only when you assign it to something or when it has to be evaluated, then the calculations are done. And this might point you in the right direction. So we have an expression object here on the first line in the last block. And that usually stores matrices by reference, because matrices might be arbitrarily big. You usually capture them by reference. This means there's a reference. And as I mentioned earlier, the calculate offset method returns a new temporary matrix. So we're capturing a reference to a temporary matrix, which is valid on this code line here, but on the next code line where we calculate the result, it's a dangling reference. And if you're lucky, your program crashes immediately and you find it. If not, yeah, it's a hidden bug. And the same thing would also happen if you capture that sum variable here with a reference. That's exactly the same thing, so no difference. The same bug would occur here. Good, now this was eigencode. I want to show now how in my library I try to prevent this, or I am preventing this. So the same code could be written in my library where you add two vectors and then calculate the norm. But I have a mechanism in place that prevents this. So first of all, you might think, okay, maybe we can prevent this by not allowing the creation of such matrix expressions. But it turns out that this doesn't work because they are needed for all the operations. Otherwise, it would get fairly inefficient if you don't do that. So we cannot prevent the creation of the expressions, but what we can prevent here, that's happening on the last line where we calculate the norm method, is that somebody calls a method on an L-value matrix expression. This is something that we can prevent, because in that case, the likelihood is very high that this matrix expression contains a reference to a no longer existing matrix. Okay, how can this be done? So we're moving back to the addition operator that I showed in the beginning, and we now need two overloads of that operator. The first one has an L-value reference qualifier here, that's the 1 ampersand, and the second one has an R-value reference qualifier, meaning we're dispatching to different methods depending on the fact whether we're in a temporary or so an R-value or an L-value named variable. And what has to be done then in the L-value reference qualified method, we simply check a static assertion that verifies that this is not a matrix expression. So if it would be a matrix expression in the L-value reference qualified method, the user gets a static assertion, because this is most likely causing a bug or can cause a bug. Then for the addition, we also have the second argument. So you're adding something to the current class we're in. And then we also have to do the same check for the other argument, make sure that it's not an L-value matrix expression that is done with the helper method up here. And again, the user gets a static assertion if that would be an L-value matrix expression. And then last but not least, the actual operation in the addition operator. I'm also showing that here we're just returning the addition of the two underlying eigenmatrices in that case. In the second case down here, we have to do a std move on this, because otherwise we would end up in the L-value reference qualified version of any of the methods that we're calling here. For example, the underlying, that's a minor detail. But I also didn't know that when I tried it out the first time. So when you're in R-value reference qualified method, you're not automatically ending up in the next R-value reference qualified method. You have to manually request that. That's also a nice feature or paper deducing this, which made it into a C++23, which can be used to write these two methods in a generic way. So you can deduce the implicit this argument to all methods automatically with that. It's a really nice paper. Read up if you need it for something like this. And again, as I mentioned, this is also an example of my slogan: if it compiles, it works. Good, this already brings us towards the end. So what have we achieved so far? So far, we've achieved full support for physical units in all vectors and matrices. This includes expressive and enforced names for vector and matrix entries. So we've seen that we now always have to manually specify what an index contains. There's no way to create a matrix without that. Second of all, we've also achieved a protection against out-of-bounds access and at compile time. So it's no longer, if you use the official library interface, it's not possible to do any out-of-bounds accesses anymore. Furthermore, we've also seen how we can come to a proper domain taxonomy or domain model for all linear algebra types. So we've seen that covariances, Jacobians, vector collections. For me, this is one of the big benefits, because when I read other people's code, this is usually what I ask for the first time. So is this covariance matrix, Jacobian? Are these vectors stored in a matrix? This is something that's, if you have good documentation, it's documented somewhere, but not explicitly part of the type, and you either know it or have to find it in the documentation. So I think it's much better if we actually annotate it in the type system and then can also do checks based on that. Furthermore, we've also achieved compatibility checks for all the index structs and matrix types for our linear algebra operations. And I explained that this is a much stronger condition than just physical units check. And we've also achieved our built-in coordinate frame tagging. So I couldn't show that today because I only have 1 hour, but I also have types that can transform between different coordinate frames. So isometries, for example, which consist of rotation and translation. And then you can also check that a vector in vehicle frame can only be transformed to sensor frame by an isometry, which goes from vehicle frame to sensor frame. So you also have a check for your transformation order that this is correct. And yeah, there are also a few more built-in checks, for example, that you can only transform points for if you have a displacement vector, then you can only apply a rotation to it. Because shrinking a displacement vector when you go to different frame doesn't make sense. It's only meaningful for points where you have to like change the origin of the coordinate frame. Good. And as I mentioned, aliasing can also be prevented. If you're interested in that, I gave a talk at CPP now this year. It's not yet public, but should be soon. That's a 90-minute talk, so you can learn about the details there. And last but not least, I think we've come as close as possible to what I consider the ultimate goal in library interface design, which is, if it compiles, it works. So before we're finished, I want to mention I work at Bosch in Germany. So we have lots of job openings, also in ETAS in York, that's in the UK. We're working on embedded systems and also driver assistance. If you're interested in these jobs, please check out the linked job postings here. We are hiring and looking forward to hearing from you. And the only thing remaining now is to thank you for listening. I'm really looking forward to any questions.
How do you test the library?
How I test the library, that's actually an excellent question. And in my longer talk, I have several slides on the topic. Because most of what the library does is forwarding to the underlying library. The actual operations themselves don't need much testing because they're usually tested with the underlying linear algebra library. But you're right, what I'm doing is sprinkling a lot of syntactic sugar on top of it and doing compile time checks. And there, the main question is how can you test compile time checks? I mean, we still have some time. I could even move over to that slide because that should be contained in the talk.
It just should be like a bunch of samples that should never compile.
Yeah, exactly. That's what I'm doing. So I have like tons of compile fail tests. This can be done with a built-in CMake feature that says, okay, please execute this test or executable. You can pass the output with a regular expression. And I'm grabbing that the output contains a static assertion in that case that shouldn't be compiling. And I have hundreds and thousands of these tests, even in a single file, of course, encapsulated with an if-def. So you have to run each of the blocks that should be invalid through the compiler. So it's time efficient, not time efficient, time consuming to do all of that. But this is what I consider the most important tests for the library. And I'm testing like all of the conditions I have for the library interface. Also that what I mentioned with a dangling reference, I also have a few checks in place there that this fails under these conditions. This is really the most important thing. Of course, the actual operations, checking that also makes sense. But I think, yeah, I don't have to test the corner cases that much because, as I said, I'm only forwarding. If that's guaranteed, then the underlying library would be responsible for that part. Yeah, so the question was whether this can be simplified by an equals operation. Yes, it could be done, but if you write position vehicle equals other position entry dx, that would be for me misleading because equals I would assume that the whole thing is assigned. So yeah, might be a little bit difficult to do it that way. I already left out the index for the assign entry because it can be inferred from the other argument. So originally I had the index mentioned twice. Yeah, there are a few things you could even imagine, like reordering the parameters of your constructor. This is something that's possible. We actually have a functionality for it, but I didn't want to build it into the native interface of the library because that might be, I don't know, I wanted to know what the order is of the indices, and this enforces you to always write them in the correct order.